we're introduced to the psychrometric chart figure in the back of the textbook for SI as well as English units. Notice only the psychrometric chart for 1 atmosphere pressure. They do have psychrometric charts for elevation of 5280 mile high. Some cities in the United States are mile high. But if you start going at different elevations, because it becomes lower overall total pressure, you just move to the computer, and the computer programs can take care of the exact elevation. If you needed to design something for 12,000 feet, some high elevation, that's the way you would do it. But don't forget that these psychrometric charts are for sea level. Sea level, and there are a lot of people living and operating around sea level. What's our elevation in San Antonio? Probably around 900, 800. Because they'll have the sea level at the airport, which is, I think, not Brooks, Kelly, probably Kelly Air Force Base. The runway there, that's the elevation. But you know, as you continue to move, where we're at is higher elevation. And if you just move further north, it just climbs into the hill country, and you gain elevation pretty rapidly. Not as rapidly as a mountain, but we're close enough to 1 ATM that we just run with 1 ATM. We went through this chart. Does anybody have any comments about this chart? There's a lot of information. How many temperatures are on this chart? How many humidities are on this chart? How many temperatures? Really 3. You got dry bulb, wet bulb, dew point. True? Dry bulb, wet bulb, dew point. How many humidities? 2. Relative and humidity ratio. So humidity ratio is over here. Line of constant humidity ratio. Line of constant relative humidity. Like that. How about temperature? Line of constant dry bulb temperature. Maybe I should stay with the color red, get a little more visible. Line of constant dry bulb temperature. True. Line of constant wet bulb temperature. True. And where do you get the dew point temperature? If I said, here's a state right here, how would you find the dew point temperature for that state? Conceptually cool it without changing the humidity ratio until it can't be cooled any further without dropping humidity ratio. This temperature right here, you can come down and read it, is the dew point temperature. A lot of time they'll say, you know, it's a wet bulb or saturation temperature. So as you come along, here's a temperature of 10, here's a 20, here's a 30, and it's a little bit of a challenge. Like this is 21, 22, 23, 24, 25, 26, 27, 28, 29. Spreads out a little bit. But you get, after you use the chart a few times, you get better at reading it. All right. And then there's one enthalpy, energy content. It's a mixture enthalpy of the moist air, kilojoules per kilogram of the dry air. Can we solve a problem like this? So moist air at 26 and 1 ATM and 80% relative humidity enters a heater with a volumetric flow rate. I'll call that AV for a volumetric flow rate, 0.47 meters cubed per second. It exits the heater at 30 degrees C, so it went from 26 to 30. It's heated. It's being heated. True? Determine the heat transfer to the air in kilojoules per kilogram of dry air. So you have a duct, you have a little heater like this. Don't need to collect a coil for fear of condensation on a heating coil. That's not going to happen. It comes in at state 1, it goes out at state 2. And so if you want the heat transfer, you do a little control volume analysis. True. And you can assume the Q dot in the mass flow rate of the dry air through the system. And you have an energy balance where you have Q dot in is equal to the mass flow rate of the dry air times the enthalpy exit minus enthalpy entrance. Energy balance. True? So lowercase q, which is Q dot per M dot dA is equal to H2 minus H1. So it's different in that mixture enthalpy. What were the units on that mixture enthalpy? Kilojoules per kilogram of dry air. That's the units of this mixture enthalpy on the psychrometric chart. You take a look, what do they want? Kilojoules per kilogram of dry air. Everything's consistent. Those are the units that we want, so it's a change in H. So what we have to do is, I'm going to switch to a psychrometric chart and put the points on. So try to remember 26 and 80% relative humidity, right? So if you come over at 25, 26, maybe I'll change it to red. There's 26 degrees C, 80% relative humidity. Here's that line of 80% relative humidity. Find where they intersect. Right around there. Then get a enthalpy. I'm going to call that enthalpy 68. That's enthalpy at state 1, H1, 68 kilojoules per kilogram of dry air, H1. It said it heated it to what temperature? 30? Did it change the moisture content by just passing it over a heating coil? So which of the two humidities remained unchanged? Phi, relative humidity, or omega, humidity ratio? Omega. So along a line of constant omega, you just go straight across until you get to 30 degrees C, right there. And now that's state 2. You try to read off 72, looks like it's 72 for the enthalpy. See how we did that? Oh, all the tediousness of those hand calcs just sort of go away with the psychrometric chart. But you have to know what you're doing, so let's jump back.
Whenever you're calculating heat transfer, whenever it's putting those words exactly, go back.
Okay.
Whenever you put them in those words exactly, you want us just to use the enthalpy of the dry air and don't worry about the moisture.
Okay. This mixture enthalpy of the moist air accounts for, it accounts for the latent, the enthalpy associated with both the sensible on the vapor as well as the latent on the vapor. You can, if it condenses out. So it accounts for it. So the equation for this enthalpy is H of the dry air plus omega H of the vapor. True? Remember that? That's of the mixture, MIX. No, most people don't put MIX. Excuse me. They just put mixture enthalpy without any subscripts. Okay. That's often a very confusing point. Some people I've seen, professionals, they call me in, hey, I'm got this question, and they're designing systems and they're using psychrometric chart, and they think that this delta H is only for dry air. And they have to do an additional calculation and add it to this energy balance for the condensation, for the for latent, any moisture condensing. It's like, no, it's included. See this term right here? That's associated with the vapor content, the moisture content. Okay, so that's very confusing. So what did I say? It was 72 minus 68, around 4 kilojoules per kilogram of dry air. And then what is the rate of heat transfer? Well, I go right back to this equation right here. So I need the mass flow rate of the dry air. How do I calculate the mass flow rate of the dry air? It's the volumetric flow rate, what was given in the problem statement, divided by the specific volume. And we're going to say this is the inlet. It enters, and it enters. So I need that specific volume of the entering air. True? Okay, so we go back to the chart, and I need that specific volume. Here's a line of constant specific volume. You can kind of see it right there. Units, meters cubed per kilogram of dry air. So it's how much volume is occupied per kilogram of dry air. It's how much volume is occupied by the moist air per kilogram of dry air. So what we do is we come over here. That's a line of 0.90. Here's a line of 0.85. True? See that? And we're trying to get it at this point right here. Well, it looks like it's not on this line, but it's on this line right here. So it's 0.87. Do you see that? 0.87 meters cubed per, because it's going between this value and that value. It's increasing, and there's, 1, 2, 3, 4, 5. So it's 0.87. True? Thumbs up if you agree. Thumbs down, or don't give me a response if you're sleeping and enjoying this class. Oh, you can't see it? Do you have your appendices? If you have your appendices, maybe you could be looking at it. Okay? So what happened here? Okay. Well, it is close enough to 0.7. Sorry if it's very difficult to see, but charts are often hard to see. So 0.47 meters cubed per second times what did I say? 87 meters cubed per kilogram of dry air. True? And so that gives us the mass flow rate in kilograms of dry air per second. Then you multiply it times this delta H, and then you get Q dot. I solved the problem before coming here. I find my notes. We find that it's about, we find that the Q dot then is around, well, this is 0.54 kilograms per second. Then multiply that by 4. Kilowatts. True? All right. Ready to go to another problem? How many people felt this problem was beneath them? You can handle that on the quiz. No problem. You're ready for the quiz right now. Don't need to study. How many people are like, what is this? Yeah, the test. How many people are like, really? This is possibly going to be on the test? Something like this?
I don't know about looking at the chart.
You have to look at the chart some more?
Yeah.
Okay. Well, please do look at the chart some. And typically, I'll give you a copy of the chart so you can actually put your pencil down on a paper and rub around and not mark it up in your pristine appendix. But you can mark it up on the exam. One will be given. So here's another problem. We have moist air at 28 degrees C, 1 atm, and 50% relative humidity. It flows over a cooling coil and is cooled until it's 20 degrees C. Try to remember these numbers. Let's jump to a chart and try to find these states. So it starts off at 28, right? So right here is 28 degrees C, this line. And it's at 80% relative humidity. And so where it intersects is state 1. And then it says it's cooled until it's 20 degrees. Let me back up. I don't think I did that right. It's 50% relative humidity, not 80% relative humidity, right? So let's jump over here and do that again. 28 and 50. So not up here. It's right there. That's state 1. True? Now, if you cool it, it's going to just be like heating. The humidity won't change until you hit the dew point temperature, but you're going to hit 20 degrees before you hit the dew point temperature. So there's state 1, there's state 2, and the first question they ask is, what's the relative humidity at the exit? What's the relative humidity at state 2? And you look at the chart, and you can see that it lies a little bit above 80% relative humidity, right? So you can't get this to 3 significant digits unless you're just super good with your eyes. But what percent, you know, be like 82%, 81% relative humidity. That's the answer to part A. And then the next question deals with energy transfer. So without jumping back and forth, what you have to do is come back up here and get the enthalpy. Maybe that enthalpy looks to be, I don't know, looks to be 59 for state 1. What's the enthalpy? Oh, it looks to be about 50 for state 2. So we can answer both of these questions. Humidity was 81% at the exit, and the rate of heat transfer to the air is H2 minus H1, which was, it's the enthalpy to the heat transfer to the air, but it's being cooled, isn't it? So maybe we want to put a negative, make sure it's a negative answer. And so it's H2 minus H1, it's 50 minus 59, it's not negative 9 kilojoules per kilogram of dry air. Enthalpy change is 9 kilojoules per kilogram of dry air. It's trying to be consistent with the wording, make it a negative. All right. Ready to solve another problem? Very similar, same inlet condition. It's flowing over a cooling coil, but now it's cooled to 13 degrees C. Last time it stopped at 20. Now it's cooled to 13. And moisture is condensed and collected using a drain pan, and then the liquid leaves at 13 degrees C through a liquid drain line. So determine the relative humidity at the exit. I'm going to jump back to, I think it's this diagram. And so we just continue. The state 1 is the same, but when you hit the dew point temperature of around 17 degrees C, if you cool it below 17 degrees C, it then will reduce the amount of humidity. Humidity ratio will go down. You need to cool it all the way to 13 degrees C right there. And so this is the ending spot right there. This is now the exit state 2 at 13 degrees C. What's the wet bulb temperature at 13 degrees C? Exit. It's 13 degrees C. What's the dew point at the exit? All those 3 temperatures are coincident at 100% relative humidity. So the wet bulb, the dew point, and the dry bulb all are the same. Okay? At this state. If you wanted to, you could see how much moisture is collected. You have to do the difference in this omega. All right? But let's read off the enthalpy here. That enthalpy looks to be around, I didn't do it that well, but the first time I did it, I had 37 kilojoules per kilogram. I think I still do. 1, 2, no, it looks like it's closer to 36. Here I'll bend it up. I think that's 37. Anyway. Different students, when they use the psychrometric chart, it takes more time to grade because somebody is, close, but they're one above and one person's a little bit below. They both get the equal credit. Right? It's just those way off. They don't know what they're doing that you have to take and remove or have the student lose points. Okay, so it goes from 59 all the way down to 37. That changes 22 kilojoules per kilogram. It's a much larger change, true? What was the temperature change between here and here? The first case. It was 8 degrees C, true? And then from 20 to 13 is another, 7 degrees C. But almost the same temperature change, but a lot more heat transfer is required because you're condensing some vapor. wringing moisture out of the air puts a higher load on air conditioning systems. Your electric bill to keep you comfortable in August in Houston will be higher than the electric bill to keep you comfortable in some other state or dry climate, San Antonio or El Paso. Okay?
So this enthalpy change takes into account the enthalpy of the liquid water that's coming out?
Yeah, because the equation was H is equal to H of dry air plus omega H of the vapor, and the omega's changed.
Yeah.
That's right. It takes into that account. And so there you go. The relative humidity at the exit, 100%. And the heat transfer to the air, what did we say it was? Negative 22 kilojoules per kilogram of dry air, lowercase q. All right. Let's press on.